Geometry in 3 dimensions. So we start again with the Common Core quote. You can read that. It basically says that 3-dimensional stuff is something using cubes and cones and cylinders and spheres for younger folks is very important. It actually very much is. That you're going to have future little engineers and chemists. Just last night, my own daughter who goes here, and she's majoring in chemistry, she was telling me about when water dries out, they dry out water, how it makes a certain crystalline 3D structure, and that's why it's less dense, it's wider than other solids, and that's why the icebergs float in the water, and anyway. So she's having to picture 3D shapes all the time in her chemistry class. So you'll have younger folks, and you'll be teaching them because they'll need to do that in their future. So here we go. So let's talk about 3 dimensions. We're wrapping up Chapter 11. Chapter 11 is our introduction to geometry. This is the last day on Chapter 11. Then we'll dive in on Wednesday, Chapter 12, where we'll start calculating things like areas and volumes and things like that. So this is the intro, like a lot of naming and getting comfortable with the basic shapes. So Part A, we're talking about prisms first off, or polyhedron. Let me start there. A polyhedron, you can read the definition. It just means a 3D shape where all the sides are simple closed curves. Polygonal regions. They're basically polygons. So basically a polyhedron is where you take a bunch of polygons and you put them together and make a 3D shape. They call it a polyhedron. What does poly mean when it's in front of a word? Many. Means many. Means many. So many-sided shape, 3-dimensional, polyhedron. The plural is polyhedra. So anyway, so let's get into the particulars. A prism, that's the if you read that definition, it's so math definitions are funny, aren't they? Here, I'll read the math definition. A prism is a polyhedron in which 2 congruent polygonal bases lie in parallel planes, and the remaining faces are parallelograms. Doesn't it? Math definitions don't sound like they're trying to help, do they? It sounds like it's written in a foreign language. Let me say it this way, and that's your job when you teach younger folks to break it down. Prisms have 2 of the same shapes on the top and the bottom. That's a prism. 2 of the same shape, top and bottom. So like we have here, a triangular prism, because it's got a triangle on the ground and a triangle on the top. Or here we have a quadrilateral prism. The bottom is a 4-sided shape. The top is a 4-sided shape. Or here we have hexagonal prism. The bottom's a hexagon. The top is a hexagon connected with straight sides. Now notice this one's leaning. I'm sure you noticed that. When they lean like that, we call them oblique. Hexagonal prism. Hexagon on the ground, hexagon on the top. So if they lean, we call them oblique. If they come straight up, like this one's coming straight up, we call that a right. Now, why do we say right? Well, because it's making 90-degree angle with the ground. So it's not the Leaning Tower of Pisa, right? It's coming straight up, 90 degrees to the ground, so we call those right. So a right hexagonal prism. Over here is a right triangular prism. The sides we call lateral faces. And then we have edges, of course. And the bases is what we call the top and the bottom of the prism. And so you have some prisms before you there on your desk, right? Let me jump to this part. Next, we want to talk about pyramids. I think you know what a pyramid is, right? It just comes to a point. So we name them by the base. So this is a triangular pyramid because it's got a triangle on the ground. This is a square pyramid because the base is a square and it comes to a point, so it's a pyramid. And then a pentagonal pyramid because it's got a pentagon on the ground and it comes to a point. So a prism has top and the bottom the same shape. A pyramid comes to a point. Otherwise, pretty much the same. Everything else makes sense. Let's do this. I made this little table because I want us to see a certain formula and a relationship that exists here. Let's go back and take that right triangular prism and let's count its vertices, faces, and edges. So we're talking about this one. Let's count its vertices, faces, and edges. So first off, how many vertices does it have? So can you tell? How many corners does that thing have? It's got 6 corners, doesn't it? It's got 1, 2, 3 on the top and 1, 2, 3 on the bottom. So 6 vertices. Let's go back and fill that in on the table. 6 vertices. How many faces does it have? Like all the different sides. The top and the bottom and the lateral faces, which are on the sides. How many total faces do you see? So we have the top and the bottom. And then how many on the sides? 3 on the sides. 5 altogether? Is that making sense? Because we have 3 on the sides and then the top and the bottom. 5 total faces. 3 of them are called lateral faces, meaning they're the sides, and then the top and the bottom. Okay, so we'll fill that into our table. And what's the number of edges? That's a little harder. How many total edges? Can you count all the different edges on that thing? Like 1, 2, 3 coming down. The way I always count edges, I just count how many coming down from the top to the bottom. 3 edges coming down, and then how many edges on the top and how many edges on the bottom? So edges on the top, it'd be 1, 2, 3 edges on the top, and 3 on the bottom, and 3 coming down. 9 altogether. We good there? So let's fill that into our table. All good on that shape? The one you have before you there? Okay, so let's do the square pyramid. Did I have a diagram of the square? Yeah. Good, perfect. You have one at your desk, and we have one on the picture. So take the square pyramid and find the vertices, faces, and edges. So fill that in. Okay, so how many vertices are you counting? 1, 2, 3, 4, 5. We good? 5 vertices, 5 points. How many faces? Yeah, because we have, here's a face, 1 face, 2 faces, 3, 4 faces that are sides, and then the base. So that's 5 faces altogether, 4 on the sides, because, has to come up the sides, 4 of them, and then 1 on the base, that's 5. How many edges does the thing have? So how many edges coming down? 1, 2, 3, 4 edges coming down. And then how many on the ground? 4 on the ground, so 8 edges altogether. We good there? 5, 5, and 8. You seeing that on the one at your desk? So let's fill that in. 5, 5, and 8. Now they're asking us to observe a formula, a relationship that exists for all polyhedron, any polyhedron. I'm not going to fill in the rest of the table. We don't have time. But let's take vertices plus faces and subtract edges and see what number we always get. Vertices plus faces, 6 plus 5 is 11. Minus edges, minus 9 equals 2. Let's try it on the next one. Vertices plus faces, 5 plus 5, 10. Minus edges, minus 8, 2. It's always 2. Somebody proved it. I don't remember what his or her name was, but you could look it up on Google, I'm sure. You would know. I didn't put the name in there. But yeah, it's a famous theorem for any polyhedron, meaning any three-dimensional shape made out of all polygons. The vertices plus faces minus edges will always equal 2. Be a good one to have on your 3x5 card for our first exam, but we'll have a practice exam before then, and I'll remind you at that time, and we'll talk about it then. All right, so did everybody get that? Was I too fast? Vertices plus faces minus edges is 2. So let's go on now to regular polyhedra. So these are super special shapes. There's only 5 of them that exist, and they're called regular. Remember what regular means? I always think they use the wrong word. It means perfect. So there's actually 5, and only 5, that's why they're so special, 5 perfect three-dimensional shapes. What do we mean by they're perfect? Well, they're made out of perfect shapes. So in other words, they're made out of perfect triangles, perfect squares or perfect pentagons. So look at this first one here. See the triangles that make up this tetrahedron? They're equilateral triangles. They're perfect triangles. But that's not the only thing made out of triangles. So is this octahedron. He's made out of perfect triangles as well, and he has 8 sides instead of 4 sides like the tetrahedron. And then we have this guy over here, the icosahedron. He's also made out of perfect triangles, and he comes up to 20 sides. And then we have the one we're most familiar with, the cube. It's made out of perfect squares. And then finally, the dodecahedron is made out of what? Perfect pentagons. 5 sides, right? Each of those has 5 sides. Perfect pentagons, dodecahedron. And that's it. That's all you have. Just out of your book. Historical note from Plato. You know, if you're taking your philosophy class, Plato, I think, therefore I am. Anyway. Platonic solids. Plato was into these things because there's only 5 of them. There's no more that could ever exist. And so he thought there was a big deal. He philosophized about it, and he thought that they were the smallest particles of the earth that have the form of a cube. So the ground of the earth is made out of cubes, he thought. The air is made out of little octahedrons. Fire is made out of little tetrahedrons. Water is made out of icosahedrons. And the entire universe is made out of dodecahedrons. He, of course, is completely wrong. But that's what he thought way back when. You know, that's, in fact, exactly what my daughter was looking at with chemistry. We're made out of, the universe is made out of other shapes. But he thought they were so special, they must be what make the whole universe. So they ended up being named after him. So they're called the Platonic solids. Dice, you'll have the same chance of getting any side to come up because all the sides are the same. And this is the only 5 shapes that exist, that could ever be made, that ever will be made, out of perfect shapes. Now, why? Why can't you make other shapes out of perfect triangles? Why isn't there something else made out of hexagons? We don't have any hexagons, right? We have pentagons and triangles and squares. Why can't you make a 3-dimensional shape out of hexagons? How do you know you can't? Maybe we just haven't tried hard enough. Well, actually, here's a proof of the fact that you never could make any other 3-dimensional shape out of perfect shapes other than these 5. I don't got time to go through that. I would love to talk about that with you in office hours. Put it on your schedule. Fridays, I'm there in my office. Go talk. Put it right now on your calendar if you want. Go talk to Mr. Heron about why it's interesting, I think, and I would love to talk about it with you. But we better move on. All right. So here's some flat versions of these. They call these nets. A net is a flat thing that you can cut out. So again, this, I really wish I had time for this. This would be beneficial for the proof, maybe not so much. But this would be great if we had time to cut these out and fold these up 3-dimensionally. This is something you should definitely do if you teach this material to younger folks. It's very valuable to actually cut these out and fold them and see them make the 3-dimensional Platonic solids that we see around the room. To actually make those out of the nets. So versions of them, and there's a proof we don't have time for. So there's just a summary of those 5 shapes. It's, for example, what's it saying here? Look at the top of this tetrahedron. How many triangles connect at the top of that tetrahedron? 3 triangles meet at every point. That's what it's saying there. The number of polygons that meet at a point, 3. How many triangles meet at the top of that octahedron? 4 triangles meet at every point. That's what it's saying here. How many triangles meet at the top of the icosahedron, the most complex shape? Can you tell? There's 5 triangles hitting at that top point. That's what it's saying right there, etc. It's just summarizing, telling you the angles, and it has to do with the angles, why you can only use these 5 and there's no others. It's actually not that complex. It'll only take about 5 minutes to go through the proof, but we better get to the homework. So anyway, that's the reason why these are the only 5 that could ever be made. It's based on the angles and what angles they need to connect up and make a 3-dimensional shape. So they're super special. So let's go on to the homework with that. To the homework we go. Identify the polyhedron. So let's just practice naming. Like, what's the name of that thing? Which one of those names is correct? clearly a pyramid, isn't it? Because it comes to a point. So it's got to be that one. Is it quadratic? Yeah, the bottom has 4 sides. So that's why we're saying, so we name pyramids by their base, huh? Now, what if on a test, you called it, because I'll put these kind of things on homework. My tests are really simple. They're just homework problems. You'll see. I'll give you a practice exam. You'll know exactly what's coming on. I aim to not surprise you. You'll know exactly. It's going to be this stuff. And I'll show you a practice exam, and it'll be some of these, and you'll know exactly. So if this is on a test, what if you put on there, what if you called it accidentally, instead of a quadratic pyramid, you called it a square pyramid? That's full credit. That's the same thing, right? I'm good. I just want to let you know. There's a million names here. That's all the same. You could call it a square pyramid, a rectangle. It's a rectangle on the ground. Yeah. Quadrilateral pyramid, rectangle. It's all good, right? So all those names are the same. Does that make sense? They're all the same thing. Just somehow indicating it's 4-sided thing on the ground, and it's a pyramid. Several names are fine. Square pyramid, rectangular pyramid, quadrilateral pyramid. They're all good. They're all right. All right, number 2. Number 2 is tricky. It was for me. I did it 2 or 3 different times on different days and kept getting the wrong answer, finally figured it out. So I think I can present it to you clearly. The first part's not bad. The first part just asks, how many cubes are there? So this is all about your ability to look at some flat image and picture 3-dimensionally. A really valuable skill for people becoming engineers. Like I said, my daughter's having to do it in chemistry right now, right? My son's doing some engineering stuff. He's having to. So little future engineers and chemists and physicists, they're sitting in your classrooms. They'll need to be able to picture things 3-dimensionally. So good exercise. So let's practice. This one was hard. Second part's really hard. First part, how many cubes? Can you tell? Sir, what do you think? So how many cubes? How many cubes right here? 1, 2, 3, 4. Right? So there's 4 in that front row that's on the bottom. Can I just put a 4 right here? There's 4 down that column, or whatever you want to call it. There's 4 down that column, 4 down that column, 4 down that column, and 4 down that column. Aren't there? There's 5 rows of 4. Aren't there? 5 rows of 4. There's got to be 20. We good there? 5 rows of 4 cubes, 20 cubes. Okay, now for the super hard part. How many faces are actually glued together? So if that's all glued together, so it's solid, won't come apart. How many actual faces, like little squares, are glued to other little squares? How many actual? This was always hard for me to get it straight. Do you know what I mean? Like if we take that's not a very good square. If we take one little cube and another little cube and we glue their faces together, that would be 2 faces glued. Every time we glue 2 together, that's 2 faces glued. Well, how many total glued faces are there? Well, let me just lead you through it. This one was super hard. I've spent hours. I probably spent almost an hour looking at it through the 3 different times I looked at it, about 20 minutes each time probably. So let me help with all that time I spent. Here's one good way I finally got it straight. So let's look at this. I'm going to do it in 3 because there's 3 dimensions of gluing. That's the part that's really hard. So first off, picture the row of glue that goes down this way. Back here, can you kind of picture it? I didn't draw that the best. Can you picture that back there? That row of gluing that's gluing that front row, that bottom front row back there. How many faces of glue are on just that row of glue? 4 and 4, 8. Do you picture that? Right? Because there's 4 faces and 4 faces that are glued together. Right? Imagine if we broke this up. How about that? What if I grabbed this front chunk and snapped it off? And we looked at the glue. What would we see? Glue on the front 4, glue on the other 4. 4 and 4, 8 in that row of glue. Is that good? So 8 right there in that row of glue. And then 8 in that row of glue. Can you picture back there if I went all the way down that row? There'd be 8. 8 in that row of glue. That top, those top two groups of 4 that are glued together. I'm just doing the sideways glue right now. That's what's so hard. There's 3 dimensions of glue. There's sideways, vertical, and then top and up and down. Well, I said vertical. Anyway, you'll see as we go. So, so row, row. So sideways, sideways, sideways. There's going to be 8 plus 8 plus 8 so far. Sideways glue rows. We okay with that? 8, 8, 8. Because it's 4 faces and 4 faces glued together in every one of those rows. 8, 8, 8. Okay, now we got to do glue going sideways. How about the glue that goes right here that glues the whole like top 8 cubes to the base cubes? Do you know what I mean? That row of glue, if we snap the whole top off, how many faces of glue would we see? 8 and 8, 16. Right? There's 8, right? There's 8. This has 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 little faces on the ground that are glued to 8 faces, huh? If we snap that off, it'd be 8 with 8. Can you picture that sideways glue? 8 with 8. We have one more dimension. If you're good with all that. Then we have the glue that goes down there. And then we have some of those, right? So if we were to snap that back or the front, how about if I was just to grab the front right here? And I was just to say, I'm going to snap that front off and look at the glue. How many faces on each would I see glue if I snap that front off? See, it's 5 and 5. Can you picture that? Let me help. Right? Because there's 1, 2, 3, 4, 5 cubes. Right? So if I snap that front, those 5 off the front, I would see 5 glued faces, and the other 5 it was glued to. So right down this piece, we'd have 10 glued faces, and then down this piece, 10 down here, 10 down here, and 10 down there. Do you see that? 10, 10, 10. And that's all 3 dimensions. We've done all 3 dimensions of gluing now. So add all those up, what do you get? This is 5 times 8, 40, 50, 60, 70. Better move on. That's a tough one. So that's a real exercise in 3-dimensional imaging and picturing, isn't it? That's challenging. All right, let's get back to some naming of these things and some numbers here. The base of a prism has insides. How many lateral faces does it have? So if you have a prism, what's a prism again? It's not a pyramid, but a prism. How would you define a prism? It's got the same thing top and bottom. Remember that? Same kind of shape, top and bottom. So for example, I could have a triangle on the ground and a triangle up top. And it's connected by straight points. That's a prism, right? That has n equals 3 sides on the 3 sides, right? The base has 3 sides, doesn't it? Here's the base right here, and the base has 1, 2, 3 sides. So the base, what's on the ground, has 3 sides. So how many lateral means the side faces. Lateral faces. How many side faces does it have? So you guys have one of those on your table there, right? You have a triangular prism. How many side faces does it have? It's got 3. So in other words, it's got the same number as it does sides on the ground, of course, huh? Each of those sides on the triangle on the ground comes up to be a side face. It's got to be the same, doesn't it? So if it's got n sides on the ground, it's going to have how many side faces? N. It's got to be the same, doesn't it? So if it had 10 on the ground, it's going to have 10 sides coming up, doesn't it? If it has 5 on the ground, a pentagonal prism, it's going to have 5 sides coming up. Okay, and then part B says, well, how many total faces does it have now? So now we mean not only the sides, the lateral faces, but also the top and the bottom. So if it has n sides on the ground, that's going to be n faces coming up, plus 1 on the top and 1 on the bottom. So what's the total number of faces going to be? Going to be n plus 2, isn't it? Little formula that way. Number 4, hexahedron. Hexahedron. Now notice they're not saying, this is what fooled me at first on this one, they're not saying it's a hexagonal pyramid. That would be a little different. They're saying hexahedron, 6 faces total. That's the total number of faces. So which one of those shapes, A, B, C, or D, has 6 total faces? Yeah, this one, huh? Because it's got 5 side faces, right? 1, 2, 3, and then 4 and 5 in the background there. 5 side faces, and then the one on the ground is the 6th face, isn't it? So this is actually a, not hexagonal. It's, what would be the name? It's a what pyramid? How would you name that as a pyramid? How many on the ground? Remember, you name pyramids by how many sides on the ground. How many sides does it have on the ground? Yeah, 5, so pentagonal. Pentagonal pyramid. And it's got 6 total faces, so it can also be called a hexa, which means 6, hedron. Notice those 2 different naming schemes. 6 total faces, hexahedron. 5 on the ground, and a pyramid, pentagonal pyramid. Is that okay? 2 different ways of naming things. So that's our answer. Feel free to stop me if you want to talk more about it. All right, number 5, we're back to this 3D imaging. What we're doing here is we're taking a straight line and we're imagining rotating it in our hands, and what kind of 3-dimensional image will appear if we do that. Can you kind of picture that? I probably should have brought a 3D prop that would do that kind of thing. Spin it around. This triangle will go to the other side. It's not very good, won't it? This will go over here. Yeah. There we go. So, and it'll spin like this and make a 3D image if you spun it fast. So which one, A, B, C, or D, will it look like if you spun it? Yeah, it's D, even though they made it kind of tall and thin, didn't they? It doesn't, but yeah, generally it's going to be a circle on the ground, isn't it? Because you're spinning it around and come up like a cone. That triangle as you spin it. Can you picture that? So again, something, in the college curriculum we have so little time where we need to fly, but if you have more time when you teach, great thing to physically do. Number 6, cross sections. So this is like slicing bread. This is something, this is literally done, engineers, calculus students, literally, my son's doing this right now in his calculus class. Their teacher just last week was talking about slicing bread for some kind of thing they're doing. They take 3-dimensional shapes and they slice them up. So younger folks that are going to eventually do this stuff, you'll really be a big help to them if you get them thinking about taking a three-dimensional shape and slicing it like bread. So if you took some triangular prism loaf of bread there, right? That's a triangular prism. And you started slicing pieces of bread. We call that a cross-section in engineering. What shape would be the piece of bread? Every piece of bread you cut off is going to be what shape? Just going to be a triangle, huh? Is that clear to you that you'll just be cutting off triangles on the cross-section there? All right. I better get to these other ones. So here's a flat shape. This is a net again. It's flattened. And we want to fold it up. We want to fold all those corners up to make it a 3D shape. Again, we're picturing from 2 dimensions to 3 dimensions. Can you look at that flat 2-dimensional image and picture what it'll become 3D? So we folded up all those corners and they meet at the top, in a point at the top. What's going to be the name of the 3-dimensional shape that we make? Is it going to be a pyramid or a prism first off? Some kind of pyramid, because it's coming to a point, right? Prism has 2 shapes, top and bottom, that are the same. This is going to come to a point. It's going to be a pyramid, not a prism, huh? Pyramid. And what kind of pyramid? Is it going to be a right square pyramid or a right hexagonal pyramid? It's got 6 sides on the ground here. 3, 4, 5, 6. So it's a hexagonal pyramid. Why is it right? Right just means it's straight up instead of leaning. So it comes straight up to the middle. So it's a right hexagonal pyramid will be made there. Okay, now number 8's tricky. It tricked me at first. I'm just telling you my experience. When I first went through your homework, I got number 8 wrong at first. They're basically asking us, hey, which of these flat 2-dimensional things, again, we're picturing from 2 dimensions to 3 dimensions. If you take that flat 2D image and you fold it all up, will that make a 3D shape or not? I looked at 8 part A there, and I said, oh yeah, that'll make that 4-sided triangular thing. And the answer is actually no. I don't know which no is it? No, this is not a net because there are no 4-sided patterns. No, that's not true. It's the other no. It's this no. This is not a net because there are not enough sides to... Yeah, it's true. Now, I kept thinking, won't that make that one special one that's on the wall over there out of the triangles? Well, not quite. Look at this image for a second, and let's go back to the other one. And you'll see what I mean. That's what I had to do. There it is. See, it's actually... There's the one I was thinking of, but it's set up a little different, isn't it? See how in this way it will work, right? You just take these 4 points, and they'll all fold up and meet at the top to make, the thing that has 4 sides all out of triangles. That one works. That flat will fold to a 3D. But back to this one. See how that's set up different? There's not one in the middle with the 3 around the sides. Let's go back again one more time. See how this has 1 in the very middle here and the 3 that are around it, so it'll work. But if you go back here, this one, they're just all 4 connected. It's not 1 in the middle with the 3 around it. Again, college curriculum, I've always got to move fast, but great exercise to actually do with younger folks is have them fold this all up and see that if you started folding that, it would just fold onto itself flat. Can you picture? This side would just fold flat onto that side, right? 1 and 2 would just fold flat on each other. And 3 and 4 also, if you fold them, they'd just be flat. It'd just be all flattened. It wouldn't be 3D at all. Now, how about B? Well, that one works. Again, we don't have time. It'd be great to actually cut that out, fold all those corners up, and you would see, yeah, that'll make a prism with square sides. So that one works. Yes, it's a net because it can be used to make a polyhedron. The other one, they say any 6-face pattern. No, not any. But yes, this one works. So I'll move on. Make that if you need to. Glad to do that with you if you want to talk about it in office hours. Number 9. Vertices plus faces minus edges equals. Well, we already saw the formula. What is vertices plus faces minus edges always equal? 2. Now you could go through it and count them. There's 1, 2, 3, 4, 5 vertices. You don't need to. How many faces? There's a face on the front. 2, 3, 4 on the bottom. There's 5 faces altogether. How many edges? You could count it. The number of edges. Edges come down 1, 2, 3, 4 edges come down. 4 on the ground. 8. Sure enough, it equals 2. It's all true. Let's move on. Number 10. Number 10. Classify each of the following as true or false. These can be a little tricky. We're trying to push through to number 13 in the next 5 minutes. Let's see what we can do. The bases of all cones are circles. Bases of all cones are circles. Is that true? Are the bases of cones circles? Well, they don't have to be exact. Circle means, perfect circle. It doesn't have to be. If you go back to the image I first gave you, I flew over it quick. See how, like, the cylinder... Now, these look like circles, but see how that's kind of a little bit oblong? And this one, that's not a circle. That's circular, kind of, but definitely not a perfect circle, huh? So they don't have to exactly be perfect circles. They can just be any closed region, is the answer to that question. So false, any simple closed curve is good. How about the next one? A cylinder has only one base. Does a cylinder have only one base? Remember what a cylinder is? Different than a cone? Let's go back. Cylinder back here. So these are cylinders. Do they only have one base? They have two. They're like a prism, but circular on the top and the bottom, huh? No, they have two. Cones only have one base, right? They're like a pyramid, but circular, right? So cylinders have two. So that would be false. Cylinder has two bases. How about C here? All lateral faces of an oblique prism are rectangular regions. That's a tricky question. What's an oblique prism? Let's go back to it. I think we had one back here, didn't we? Right there, yeah. Here's an oblique prism right here. See this? There's an oblique hexagon. Oblique means it's leaning. It doesn't come straight up. So a right prism or a right anything comes straight up. An oblique shape leans. So this is an oblique prism. So what kind of shape are the sides? That's what they're asking about. Are they rectangles? Well, not quite. They're kind of leaning. So in other words, the sides, instead of coming straight up, that would be a right shape, right? Instead, they're more like this, aren't they? This is oblique. What's that called? What kind of shape is this called? Parallelogram, huh? See how the sides are parallelograms on an oblique shape because of the lean? So an oblique shape is leaning and the sides are parallelograms. Whereas see the right one, they're perfect rectangles, aren't they? On the right hexagonal prism, they're perfect rectangles. But on the oblique one, they're parallelograms. So we go back and say, okay, so that would be, they're rectangles? No. On an oblique one, they're parallelograms, not rectangles. We good there? That making sense? Looks like